contribute to a more heating sector. My name is Carolina Holmberg. I work at Energiforsk as the area manager of our heating and cooling area, and I will be the moderator of this seminar that will be held in English today. So today, the results from 2 research projects will be presented. Both of them have been financed by Thermo, which is a research and innovation program within the heating and cooling sector that is run by the Swedish Energy Agency. And this webinar will be recorded and published on the Thermo Innovation website. So it will be available for you if you want to look at it again, or if you had any colleagues that couldn't join us today. Our 2 presenters, they are both from the Royal Institute of Technology, David Rolando, researcher at Applied Thermodynamics and Refrigeration, and Kian Wang, researcher at the Building Technology and Design. David and Kian, they will present for about 15 minutes each, and after that we will have a joint question and answer session and discussion, and we will finish no later than 10. Questions from the audience is more than welcome. And for questions, we will use the chat today. We will save the questions to the end, as I mentioned, but you're welcome to write the questions in the chat during the presentations. So please start by writing who the question is directed to, and then try to keep it short and concise. While David and Kian presents, you in the audience cannot use your microphones or camera, but you will have the possibility to do so during the discussion session later if you want. So now I welcome David to present his project, Digitalization and Internet or IoT Technologies for Heat Pump Systems. Welcome, David, and please take over the screen sharing.
Thank you, Carolina. I'll share my screen.
And we see your screen, perfect.
Thank you. Good morning, everybody, and thank you for joining this webinar. In this short presentation, I will give you an overview on the research project called Digitalization and IoT Technologies for Heat Pump Systems that we run within the Thermo program. First of all, this project was carried out within an international collaboration, an international annex called Annex 56, promoted by the International Energy Agency, the heat pump technology, part of the International Energy Agency. The Annex 56 was called Digitalization and IoT for Heat Pumps. And as you can see here, we focused on the 3 main topics: interfaces, data analysis, and services and business models. And it was an international effort, an international collaboration. You see here the list of the countries that joined this research annex. You see here Austria, Denmark, France, Germany, Norway, Sweden, and Switzerland. This annex was coordinated by AIT in Austria. And from Sweden, it was a joint collaboration between KTH and RISE. With this annex, just to define what were the boundaries that we moved on for within this collaborative research, we moved into a boundary that you can see depicted here, where we explored the challenges and opportunities of digitalization and IoT technologies for heat pump systems in the case where the heat pump is not just, of course, just a single unit, but where potentially several units are communicating to each other, and the heat pump is integrated in the as one of the subsystems in a building. So here is the boundary where we moved on. I was coordinating the work for the delivering the report over the so-called task one, dedicated to the state of the art. And in that report that I invite you to read, and I will give you more direction where to find it later on. We started with some it's important in a way, and the definition of Internet of Things that probably everybody heard of. But it's important to focus on the definition and what this implied for the industry and for this type of development of this type of technologies. So in this definition, it was from 2005, there is a remarked shift in paradigm between what was conceived until that time, we could say, as communication between machine to machine and between person and computers. At that time, there was this idea that the communication was extended more broadly to things. And then in that way, things in a broader sense, not just specific devices, would have been assumed as capable of transmitting information and communicating information to each other and to other machines and to humans. And this marked a shift in the industry, where also buildings and all the subsystems in buildings were involved. And this shift in paradigms marked the beginning of a proliferation of technologies and communication technologies, for example, and consortium that were very exciting and very broad, and also very challenging to figure out. Here you can see just one representation of different type of technologies and consortium regarding communication technology. And here you can recognize some names probably. For example, regarding what they are, how they are called, industrial Ethernet field buses, like Modbus, which is quite, let's say, old communication protocol, but still very relevant today. And more modern communication protocols like KNX and BACnet, for example, and other, let's say, web-based communication protocol like AMQP and MQTT. For example, that, let's say, were developed after this shift in paradigm. As you can imagine, from this broad range of technologies and solutions, it's really impossible to pick a winner. And at the same time, it's not really fair also to answer just it depends, when you want to understand more what you should adopt for your system. Answering just it depends, it would be a little bit disappointing. So what we have done within the annex, just to clarify what is possible to do with these solutions, we collected a number of use cases. So all the countries involved in the annex collected a few use cases. 44 use cases were collected in total. They are divided in two separate types: product and services and research projects. And they were divided or categorized into these 5 categories. The idea with these use cases, so with the idea of having these use cases easy to browse and be as much informative as possible, we define this template, this framework, so that to which the use cases were first framed, and we had one fact sheet per use case produced. And on the Annex 56 website, you can browse the fact sheets by type and by categories and by countries. And the fact sheets, as I was saying, they are just 2 pages with a very straightforward summary of the use case. And each fact sheet contains also the contacts of the key person for this for each project, so that you can reach out in case you want to know more. Just to give an example and not to be too abstract, I bring here the example of the ZEB Lab in Norway, Zero Energy Building Laboratory in Norway. You find the fact sheets with the short summary of this project on the website, and then in the rest of the deliverables from the annex, you find many more details regarding the data infrastructure, for example, used. And there you find an example on how the data infrastructure was designed and what type of communication protocol are employed in this specific case, where you have, for example, air-to-water heat pumps in combination with the PV system. In that case, they implemented a data infrastructure that is based on a time series database in FluxDB, and the main communication runs through the BACnet automation controllers and subsystem protocol. Some subsystems are communicating through Modbus and MBus. This is just an example. You find the other 43 in the fact sheet. But also in this annex and in this project, then each country carried out some specific tasks. And for example, in Austria, there was a manufacturer survey that was promoted by the Austrian Heat Pump Association. Was circulated. It was consisting in about 50 questions, and was circulated through the affiliated companies of the Austrian Heat Pump Associations, and a total of 16 companies participated to the survey. And you find the results in the report. Here you find on the right just an example of the type of questions and the type of results and how it was formulated for this survey. And it was clear from the results of this survey, for example, that there are some clear challenges when it comes to digitalization that are related to data security, the lack of data protection guidelines, and the fact that digitalization also implies an increased complexity of the system, and the lack of qualified personnel that comes when you want to embrace the digitalization of your system. At the same time, I personally run from the Swedish side of this, let's say, international specific tasks. I personally run expert interviews where I involved heat pump manufacturers, IoT companies, the Heat Pump Association, and consultants. And it was not performed in the structured as a survey, but it was more like structured as a chat with the predefined questions, so that we went in principle through the question first. And actually the result from that experience was that there was full agreement about, of course, the potential that comes with the digitalization for heat pump systems. There was also agreement that there is a perceived and also a factual lack of guidelines that most of the times leave the actors in the industry a little bit uncertain on what path to take for moving forward towards the digitalization. And the need of demonstrators was also something that was pointed out during the interview, and was common by the people that I interviewed. And curious enough, similar to the result from the Austrian survey, for example, the main motivations to introduce heat pump products in the heat pump systems were similar, especially service and repair improvement was one of the top ranked ranked answers, also in the Swedish case. This is just an overview on what was specifically carried out in the task 1. I touched only briefly what was done in the other reports, but I invite you to go to the Annex website and browse all the reports. There are 4 reports in total. Other than the task 1, there was a task 2 connected to interfaces and platform. There was a task 3 dedicated to more specifically to data analysis, and the task 4 was a report was dedicated to business models. That was the international collaboration part of this project. But then more specifically in Sweden at KTH, we run an activity that was related to digitalization for heat pump systems, and more specifically to the development of data-driven soft sensors. Why that? So in the last few years and in previous projects as well, we noticed that heat pump systems today are equipped with sensors, so data is not lacking. The problem is that most of the times the quality of the data and the design of the data infrastructure for these systems is not always satisfactory, to put it in this way. And the issue with this is that you have incomplete set of measurements, and you have a design that oftentimes prevent the elaboration of even simple tasks like tracking the system performance. And for this reason, and this actually was also, let's say, reflected relatively recently in public. This is an example from a newspaper from a newspaper from 2021 that was marking the fact that data is not missing today, but we are not using it properly. And the idea was we developed a full PhD project out of it with the idea of considering we're taking the incomplete set of measurements from a heat pump system, try to enrich it with the advanced modeling, and try to figure out what is the potential for enriching incomplete set of data so that we can retrieve meaningful information out of it. The potential for this activity is multifaceted, in the sense that we want to work with data sets that have been collected so far, maybe over years, and the information is covered because, again, the design was not performed properly. For example, the data set could be not complete for other reasons. And with the combination of advanced modeling to the incomplete data set, we want to show that it is possible to give added value to the data collected. At the same time, for new systems, there is a potential enabled from this type of activities and from this PhD project especially, that is related to the fact that you can optimize the cost of your monitoring system if you have a way to develop soft sensors that can, in a reliable way, replace potentially cost devices for your monitoring system. And this would enable services, for example, connected to performance degradation and fault detection, that oftentimes requires a full monitoring system deployed. From previous projects run at KTH, we know that fault detection from this project were the reported faults to heat pump manufacturers was collected, contrary to what it could be expected, the control and electronic faults were the ones with the largest share among all three types of heat pump unit that you can see here. So this activity, for this reason, we believe that this activity is very relevant to enable services that can help the fault detection topics. I cannot go into details of the results here, but for example, in the first publications from this PhD project, we compare the potential of three modeling approaches and a combination of three modeling approaches. And we found out that, for example, that artificial neural network have a huge potential, provided that the collected data comes with a reliable level of accuracy. And I cannot go into details about this, but just to mention what we have done regarding the dissemination of these activities. Here you see the PhD candidate, that is Jansson. The PhD project is still ongoing. We had two journal publications out of this project. You find here a QR code, and I can also circulate the links if you want to know more. These activities and this project was presented also at the International Refrigeration Conference in Paris in August, and it's been presented this week at the International Conference on Applied Energy. The project will finish at the middle 2024. So I invite you to follow up for the final results of it. And this was all from my side. Thank you.
Well, thank you, David. Very interesting, and we'll keep on following for sure. As I mentioned during the introduction, we take questions today in the chat. I know Zoom also has something called a Q&A function, but don't write your questions there, because if you do, I will not see them. So if you have questions for David, please write them in the chat already, and we will try to get them answered for you later. But before that, we will listen to Kian present his project, Hybrid Control for Next Generation Heating and Cooling. So welcome, Kian.
Thanks, David, and thanks, Caroline, for the instructions and also the presentation. Please let me know if you could see my presentation.
We can see it, but it's not in presentation mode.
In presentation mode.
Do you know where? Okay, now something is happening.
Is it better now?
No, it's the same.
Okay.
So if you
We'll stop sharing and sharing the screen again.
If you, I don't know if you have two screens right now.
Yeah,
you might want to change which one is.
Yeah.
Okay, now we still see your notes.
Okay. I will share my screen, complete screen to see.
If you try to press that for the beginning, what happens?
Ah. Is it okay? No.
No. If you press from the beginning at the you had in the upper left corner. something called slideshow from the beginning. I think maybe if you press that one, it will work.
From beginning, yeah?
Yes, try that one. Okay, nothing is happening. Do you want me to try and share your presentation instead?
Yes, please. Maybe that's a bit easier.
Then I will open it. And I will need 1 minute instead. In the meantime, you can think of questions for David. Okay, let's see. I will share my screen. Let's hope that I can make this work instead. How does this look for you?
No, same problem as before.
Really? Okay, because it doesn't look like that on my computer. In that case, I suggest, Kian, that you will share your presentation yourself, and then you will try to minimize the pictures at the left bar.
Yeah.
Okay.
So,
this was very surprising.
yes, sorry for the troubles. And I guess I will just maximize the slide.
Yes. Perfect. Or as close to perfect as can be.
Sorry for this. Yes, I will start with my presentation, and I'm from also KDH, Department of bidra and skapa. And today I will talk about the hybrid control we have been working on for the next generation of heating and cooling networks. This is also developed as a PhD program, and actually one of our PhD students are here in the audience. Before I start, I would like to first acknowledge the team who has done the work, the PhD student Yanja, and also we got support from other researchers and postdoc researchers and our research engineers who has been contributing in this work. More important, of course, is that we have also created sister projects with one of our European projects that is funded by the European Union, called Hypergrid. And we want to also develop some synergies at the same time to collect data and see if our solutions in Sweden can be also making an impact to the European market when it comes to heating and cooling, in particular district heat. So this project has been very much motivated by the background of the transition needs that is putting up on the European market when it comes to district heating and also local heating and cooling networks. For example, the transition toward the fourth to the 6th generation of district heating. And maybe you have already heard that the EPBD has been recasted recently, and where the smart readiness for buildings has been brought up. And this is a strong push for us to really transition the current building stock into smart.
Sorry, Kian, have you switched slides?
Yes, I switched slides.
Okay, because we cannot see that. So
okay.
maybe you're switching at the wrong
yeah, maybe I
window.
Yeah.
Okay, great, thanks.
Yeah. Yeah, this is the acknowledgement I was talking about. Then about the background, we continue with increasing need with integrating renewables in the heating and cooling networks, because there has been a lot of discussions that how we can actually couple the energy networks in terms of both thermal networks and the electric grid. In this case, we want to utilize the thermal asset as some flexibility potentials to release the grid pressures. And with all this background, we realized there's a big challenge and problems we need to solve when it comes to controls. And this is sort of how the project has been born and developed. In principle, the project has developed within 3 stages. The first one is to understand the load. Why understand the load? Because, for example, in the electrical grid, load analysis has been long developed to understand this. But when it comes to couplings of networks, the load becomes a little bit different because electric load and thermal load has very different response time. And also, so far, we realize that many of the load analysis has been very much focused on case-to-case basis. So the ambition here is really to understand how we can generalize the method, use different, say, machine learning method or data analysis to see this kind of coupled load, and also, of course, to achieve better predictions and understanding of the load, to see what other actually flexibilities we can explore. The second one, of course, when you have the load, you want to see what other potentials to integrate different renewables into the current system in order to control them. Because as we said, control becomes a very challenging problem when you have many renewables that are intermittent and need to be integrated as a system approach. So here comes with technical and semantic interoperabilities. Both means how the configurations should be designed when the system becomes coupled, and how the data should be more interoperable. And the third stage is the final stage. Our ambition is, of course, to develop some digital twinning concepts that can integrate smart control strategies into this to perform code simulations, and of course, to understand virtual to physical transitions of such kind of complex system, and enable a representational model for the bidirectional flows in terms of data. And in this project, we want to highlight one important challenges and also a need that such data-driven approaches, we really want to co-develop with stakeholders, because we want to make sure the result can be useful, for example, for the utilities, for the building owners. And also we want to understand that how such communication can be done better in terms of in the future research project to really understand this kind of results and methodologies we have developed is of use. So as mentioned, this project has been also co-financed by European Commission, and one of the first step we have been considering is to select a typical use case. So here, for example, is a project we have been running, and we have selected one of the projects pilots in Austria. And it's an interesting pilot we start with because it has a local, say, CHP network. So it provides district heating and cooling locally. And also there are many different possibilities to integrate renewables, for example, PV systems, heat pumps, and different thermal storage and batteries are possible. And also on the other side, we already installed different IoT sensors and energy meters, so we can analyze the data, say locally at KTH, to really understand what are the different scenarios and how the code simulation can be developed through such use case. And in the past, say 2 years, we focused very much on different analysis for the load flexibilities when it comes to coupled network for the future heating and coolings. The first try we have done is to use artificial neural networks. This is, of course, quite common. That is the basis of machine learning. And we want to see how the, say, short-term prediction model can be developed. In this study, we select one use cases from, for example, typical Scandinavian climate in Shanghai, and it's different buildings that has been, say, district heated, use current district heating network with rather high temperature. And we realized that actually by rather simple neural networks, it's possible to achieve higher levels of accuracy than our conventional method. But of course, this is very much relying on how well the data you can get, as David said in the previous presentation. So we want to bring up this a little bit more to see, for example, if the data quality is not nice enough, or if there are other alternatives to understand the load better with limited data qualities. So in this work, we continue with the previous work and using similar data sets in the same district heating and climate. We developed a new methodology, or we modified the first type and used more data pre-processing processes to deal with this varying quality of measurement. So clustering method plus AM model was used as a methodology to analyze this kind of data. And actually this paper has been published, and the results are rather good, we believe. And we can actually understand this kind of load flexibilities in a Scandinavian climate and the current district heating, say, data sets. But then we realized a challenge during the development, because many of these studies were based on, as we said in the beginning, the case studies. It's very important the methodology and approach we have developed can be generalized, because we don't want to develop a new method every time when it comes to a new district or a new building. Then we continued with this work and trying to develop a more generalized or general load flexibility analysis approach by combining many different type of data sets in different climate, different even building types, and different district heating status to see if this kind of machine learning approach can deal with variations of loads in a more generalized way. So of course, validation is very important here to make sure whatever method we develop is verified, and this can be utilized for different utilities or different climates. In this case, we developed the validation method both in parallel validation. Here means that the model, we want to check if it's robust enough to predict the load for the same building, but different years. Why? Because, for example, building has been renovated, or there has been different changes of the building, but we want to see if this kind of approach can predict well. And another one is vertical validation. You can see here is that if the model is generalized enough when predicting load of on-trade buildings, because when you train the data set, you need different times. Then you need another time series data set to validate it. So we want to perform both different approaches to see if the method is good enough. Then this is ongoing work we just finished this year, and we could see that by validation, we can actually achieve rather good predictions and analysis of the couple of loads from different climate building types. So this is a good finding. We have found that by using such data-driven approach, it is possible to analyze the flexibility potentials and provide the basis for the next step of control, because you can predict the load and analyze the load more accurately now. And this kind of work we try to develop further is that because the previous approach we have developed is very much focused on individual building, but of course this is not realistic enough, because district heating is usually heating a district or on aggregated levels. So then we developed into a direction that how different buildings in one district should be coordinated in order to have the aggregated flexibilities. So this is also the ongoing work we have been focusing on, to see how buildings can coordinate with each other, because each building's flexibility may not be the same as the aggregated flexibility. So there need to be some optimization performed in order to see how we can manage the load to see the impact to the district heating network and power grid. And then, of course, when you have a district, you want to develop co-simulations and network optimization to see what are the potentials to integrate, say, renewables, for example, heat pumps or PV systems as a node of this coupled network. So we have been in collaboration with industry partners who are experienced with network planning. And the next step is we want to optimize such coupled networks for both thermal and electricity network to use steady-state thermal network simulation, quasi-dynamic thermal network simulations and achieve coupled network modelings. And particular here, because for the future generation of district heating and cooling, the storage plays an important role, because to increase the flexibility, we have to first understand the load, but also understand the capacity of storage in terms of both thermal storage and batteries. So in the next step for the coupled network, we want to focus very much to see what are the potentials and benefits to integrate heat pump and storage solutions as this kind of coupled networks. For the digital twinning concept, we realized a lot of challenges if you really want to develop a digital twin, because the digital twin here, we are not really focusing on the visualization part, but rather the data digital twin. Because as you know, there are different manufacturers of heat pumps, and different utilities have already established platforms and way of operating the data. So actually it's not lacking of data. So I agree here with what David said, that it's not really lacking of data, but it's lacking of interoperabilities. Because when we have many suppliers of data, how you can really combine this data and make standardized or normalized data models in order to run the twin simulation, because you are using different languages. And here we have been very much starting with using ontologies to solve this problem. For example, we had the first try. You see a simple and typical Swedish heating network ontologies that is using FTX system with PV and heat pumps. And we found the relationships of the data models. This is some preliminary results we have studied. For example, the ontology for the heating network that is connecting different ventilation system, which actually is FTX here, and also connecting to the thermal storage and heat pumps. For the next step, we are very much interested, of course, to develop new control systems, because we did some previous literature review about what are the really technical challenges when it comes to controls. And there are quite many limitations when it comes to existing control system, because fixed rules, regardless of which type of rule-based controls, it's very much not technically flexible enough to operate this. And also the complexity, as we mentioned, is a big problem. And we want to also improve the efficiency of the control system, so you are not fully relying on huge computing power. In this case, we perform a deep analysis and literature review. What are the promising, say, future directions we should focus on? And one of the solutions from the existing studies are for example, integrating reinforcement learning in such kind of control algorithm development. But we also found some limitations there, because for the community of more into control and machine learning, reinforcement learning was understood in a little bit different way. Because we need to make the control very practical for the buildings that actually can perform it efficiently. And for example, for such kind of learning, the building to generate a lot of data and also different type of data rather fast, but traditional reinforcement learning is only able to cope with this kind of data generations. But for buildings, this is not really realistic. And also we can choose, of course, simulated data or synthetic data to train the model. But of course, then the result will be only suitable for the simulated building or simulated energy system. This is not useful enough for the actual building, because the building is very complex. And in this case, we found some interesting solutions that could be combining different building sets to really train in a group to see how such kind of control can be developed. So this comes to the more direction of transfer learning, to see if transfer learning and meta learning can solve this problem. For example, using multi-agent learning. The reason is that when you have different buildings, different data set, you can actually meet the data requirement for the reinforcement learning and see how this can actually develop robust control strategies for the building. And a little bit next step of research. We have divided the future research into, say, two aspects. One is more theoretical analysis. So we want to see theoretically if this problem can be solved and integrated with different learning methods. For example, encoding the human knowledge into the control systems to see if this is theoretically possible. And the second part is, of course, more interesting. We want to test and validate in different living lab environment, especially when the thermal storage or another type of thermal assets for flexibility can be proved or verified. In this case, we are collaborating quite much with different living labs in Europe and also in KDH to see from an engineering perspective if such coupled network can be controlled and developed as a future digital twin platform. So researchers and engineers can run co-simulations to explore. So this is my presentation, and hopefully it's clear enough for you.
Thank you, Kian. And yeah, we apologize for the technical programs, but I think it worked out fine anyway. I saw we got some suggestion in the chat of what might be wrong, but I think it worked. We have a few questions in the chat already. I think I will give you just maybe 1 or 2 more minutes to formulate your questions if you haven't written them. And start by asking you a question myself, both David and Kian. If you could just try and summarize really short, what are the main challenges or opportunities, if you want to be optimistic, regarding the digitalization? David can start.
Yeah, I would gladly reiterate on one point that I mentioned, and also Kian actually mentioned in his presentation. And the point that probably is a public domain is the fact that data is not missing. The challenge that we face today is that data is not missing, and technology is not missing either. The issue that we have most of the times with having solutions for digitalization solution for complex systems is within the interoperability of the systems. And to that regard, the lack of guidelines and the issues with the security, as it was mentioned in one of the questions that I would answer, and the data protection they play a major role today with the hindering, in a way, the digitalization today. And it's not just a heat pump issue, I would say, of course.
Okay, Kian, do you agree or?
Yes. Actually, I also present similar message as David said, because when we look at the data, because if you want to run any kind of machine learning, you need a lot of data. So we have been really looking at the data resources in the past, say, 2 years. Data is not missing, and also we do have a lot of technologies there. But the problem, I would say, that first is system integration. So we really need to make sure the system performs as a whole instead of focusing on small individuals. So we need to have this holistic view of how systems work together. So then interoperability, of course, is a key challenge, because you want to make sure they are married, you know. And the second thing is that I would say the communication as a summary, not communication as a technical perspective, but also the communication between researchers, industries, and public, because we really face great challenges when we try to engage different stakeholders in a project. For example, say if we want to disseminate the results and we want to have some questions, it's not easy. It's not easy to just engage stakeholders. We really need to have a common understanding that what is the value of such kind of research and what can be used for the society in general. This means that we need to have more communications, because in order to co-develop such kind of data-driven methodologies, we must have a good understanding and open mindset from both sides, that researchers are willing to listen to the challenges of the utilities, and maybe utility can open up a little bit to see what are the key challenges outside the core business. So we need to also have a little bit understanding from the financial incentives. For example, if we want to transition such core business into a little bit different directions, what are the incentives and business will look like? In this way, maybe we can open up a little bit more communication to make sure such kind of research has an actual impact to the society.
Okay, great. Thank you. We have some activity in the chat. The first question we got is for you, David. It's from Svante Monje. The question reads, have you considered aspects on data security and communication redundancy in this project? And Svante, if you want to have a follow-up or want to comment when David answers, it's okay for you to just unmute yourself, just so you know. But David, the question was directed to you, so do you want to start?
We consider aspects on the data security. You find data security covered, I would say, in two parts of this project, considering the report, just to orient on the points. There are a few of the use cases that we presented that cover specifically data security issues. And there is also section 3 of the Task 1 report that is on data security and on aspects that are covering both data security and the data protection issues. And on top of that, I passed in the chat the name of the project that was run by RISE called SLAV. You can see in the chat the full acronym that was specifically dedicated to data security for heat pump systems in grid-related projects.
Great, thank you. And we got a thumbs up.
Yeah, thanks.
We have a question also from Willem Masiotti Pallard. It's for both of you. The question reads, is error in variables an issue when training models? For example, the fact that noise in input variables lead to a biased optimization. Do you want to start, Kian?
Yes, I can start. Maybe David can add, because I think I understand a little bit of problem here, William said. When we exercised, for example, when it comes to the load or coupled load, we do have quite much issues with white noises, because it depends on the energy meters. If they were installed 12 years ago or a decade ago, you will have we still are receiving many, say, interesting or jumping data from different, for example, living labs, and it doesn't make sense sometimes. So I would say that even, say, IoT sensors may have many problems, and it may give some completely wrong or data doesn't make any sense. So I think what we have tried in the project, for example, in a paper we published, is really using data pre-processing process before you throw in machine learning or any kind of training and exercise. I think one smart idea could be really do a good pre-processing and clustering method. For example, you check how the data and white noise look like by giving a little bit different method to pre-filter the bad guys and focus on the guys a little bit making sense. So this is what I have learned from the previous experiences. pre-process the data.
David, do you have anything to add?
Yeah, not much to add. It's a relevant question and a relevant issue, and I agree in general with Kian answer. In general, it is an issue, and it is despite the fact that there's that accuracy of the measurements is difficult to track. It should always be in the best practice, let's say, list of any data-related analysis. And yeah, your question, Willem, is absolutely relevant.
Okay, I hope Willem is happy with the answer. I am. We have 4 more minutes until we have to close up for the day. Since I don't see any more questions in the chat, I'm going to ask you, David and Kian, do you have any final words that you want to send out to the audience before we close this event?
Yes, maybe I can add just one sentence to summarize what we have learned so far from working on the project. I hope that, of course, this section is very much about digitalization, but I hope that people are interested in this energy or heating cooling sectors also can work a little bit more with the hardware part, because there is some imagination from people that digitalization will solve everything for the energy systems or heat pumps or PV systems, which I think it's not fully the truth. We still should understand the hardwares very well, like how heat pump works, how PV works, how the building works. This is one key message that I think we should agree, and really then the digitalization comes into the picture to solve whatever problem we have. So, but the foundation is important, and for energy system, we'll work with hardware.
Thank you. As I mentioned before, David, did you have anything? Any final words?
My final word, I invite again to check the deliverables from the annex and the project. I will make sure that the links in the shared presentation will be clickable, so it would be easier, but I want everybody to check that.
Perfect. That's what I was going to say also. You will get these presentations. They will be added along with the this video. We're always looking for collaboration, so don't be shy to contact Kian or David to discuss this further. We actually got a question in the chat again, and we have 2 more minutes. So I don't know if it was who it was directed to, but the question reads, how would you deal with challenges in the system, for example, when a district heating system?
Yes, I think this is maybe a question I should answer. I think it's a very relevant question.
Then you have 1 minute, Kian, to answer this question.
So the question put it there, it's actually correct, because significant load distributions or changes, the